we have learned how the kinetic constant relates to different factors. Some of them can be changed, such as temperature. Others cannot be changed as much, which may be implicit to that specific reaction. This is the Arrhenius equation, and we now know how to calculate the activation energy, and that's fine. Let's try to, however, go a little deeper into the understanding of some of these two physical factors that are implicit to the reaction. So think of this specific reaction. Nitrogen monoxide reacts with nitrogen trioxide to give two molecules of nitrogen dioxide. How is that reaction interpreted in terms of this pre-exponent factor A? Well, we have said that this could be the number of collisions. What do we mean by that? Well, think of that these two molecules can collide in very different ways. Some of those collisions will not be effective. So this one, for example, is not effective. This one is not effective either. This one is still not effective. And finally, no, this was still ineffective. And finally, this one is effective. So out of, in this case, we just showed you 5 pictures. One of them is effective. So that frequency factor, the number of collisions can be factorized in terms of the actual number of collisions multiplied by a factor that is just the probability factor that tells you how many of those collisions are going to have the right orientation. And you can think that the higher the complex your molecule is, the more number of, the lower the probability will be. So the higher the complex the molecule is, the lower will be the probability that that specific collision is effective. So let me just give you an example. If you are thinking of, I don't know, typical acid-base reaction, well, sure, this OH negative needs to subtract the hydrogen from here, but it can definitely collide with many areas of this ring that do not lead to products. So again, this is what we mean by the higher the complexity of the molecule, the lower will be the probability that multiplies the number of factors. This will all be factored in to this pre-exponent factor that we will say that it's characteristic of the reaction and more or less constant with temperature. We know that it's not exactly constant, it depends on the square root of temperature, but we're going to consider it constant. So, and this how we are going to interpret that. The A is the number of collisions with the right orientation, and the exponential part, it is the fraction that contain reactive collisions because of the energy. The factor that contains effective collisions because of the orientation is already into A. This exponential factor is because of the energy. So, as you well know from the kinetic molecular theory, the higher the temperature, the higher the speed of a molecule, or if you will, the higher will be the number of molecules that contain the necessary energy. So if for a reaction molecules need to have at least this much energy to react, as you see, the higher the temperature, you will have a much larger number of molecules, or a larger fraction of molecules that contain enough energy to go into products. So this can all be summed up in what is called the transition state theory. And to understand the transition state theory is very useful to put it in a plot where this is energy and this is the progress of reaction that goes from reactants to products. And if you do this, this would be the necessary energy to surmount. Of course, reactants and products coexist all at the same time, but notice that this is the necessary kinetic energy. You will have all this extra energy from reactants that products may not have. Therefore, you can expect that the activation energy, when you have an exothermic reaction, the activation energy for going forward is, in this case, smaller than the activation energy for going backward. In other words, the barrier when going from left to right, as you can see in the graph, is smaller than the barrier when going from right to left, or from products to reactants. The peak of this mountain is called the transition state, or also called activated state, okay? And it's characteristic of the reaction. It tells us a lot of information about that reaction. So, how can we connect the activation energy with enthalpy of the reaction? Notice that when your enthalpy of the reaction is negative, you have an exothermic reaction. When the enthalpy is positive, you have an endothermic reaction. Okay? In this case, because the products are at higher energy than the reactants, this is an endothermic reaction. So we have to identify what magnitudes number 1, 2, and 3 describe. Notice that number 3 is the barrier that it takes. Number 3 is the barrier that reactants need to surmount to reach products. So number 3 is the activation energy. An activation energy going forward. Number 2, if you notice, is the necessary energy that products need to pass or to have to reach reactants. So 2 is the activation energy going in reverse from products to reactants. And finally, 1 is the delta H, and you notice that you can calculate the delta H, the activation energy for going forward, going forward minus the activation energy going in reverse. In this case is positive because the activation energy going forward is larger. Therefore, you can connect these two things, the kinetic parameters such as the activation energy, with thermodynamic parameters that tell us the stability of reactants and products. In this case, then 1, 2, and 3. 1 is the enthalpy, 2 is the activation energy reversed, and 3 is the activation energy forward. This is our correct answer.